next, we have Professor Zhen Yuan. And so before that, let me introduce Professor Yuan. So Professor Zhen Yuan is an associate professor with the Faculty of Health Sciences at University of Macau, which is very close to Guangzhou. And he's also the director of Center of Cognitive and Brain Sciences. So before joining University of Macau, he had worked as an assistant professor with the Arizona State University and research assistant professor in biomedical engineering department with the University of Florida. And his academic investigation is focused on cutting edge research and development in laser, ultrasound, and EEG fMRI related biomedical techniques, as well as their clinical and preclinical applications in neuroimaging and neurosciences, and particularly in molecular imaging and cancer. He has received national and international recognition through more than 200 publications in his field. So today, he will be sharing with us on the topic of photoacoustic imaging guided cancer diagnostic. So let us welcome Professor Yuan.
Okay. Thanks, Pierre, for the kind introduction. Dear colleagues, friends, and audience, good evening. Thanks for being with us. I think I need to share my screen. I think, okay. Can you see my PPT? Okay. I think our speaker actually have delivered a wonderful talk. I think across biology and chemistry, nanomedicine, and also technique, right? It's wonderful. I think I learned a lot from from them. Their work really impressive. And okay, today I will be talking about the photoacoustic imaging guided cancer diagnostics. I'm Zhen Yuan from the University of Macau, and actually my research actually focused on three perspectives. The first is focused on the first one is technique, right? Biomedical optics is imaging techniques. We develop a lot of imaging setup for brain imaging and also cancer imaging. The second one is optical molecular imaging. We also develop a lot of probe, including nano probe for preclinical study and also very basic biology study. The third one is actually I started my this kind of direction after I joined UM. Actually, I have been working on that for nearly 7 years. It's a neuroimaging. I think I use the EEG, FNIS, and fMRI to do a lot of cognitive neurosciences and also AI, artificial intelligence. So I give a brief introduction to my lab. Actually, my lab focuses on two perspectives, right? One is molecular imaging, particularly optical molecular imaging. The other is neuroimaging. For optical molecular imaging platform, we have a bunch of homemade and also commercial imaging setup available in my lab for in vivo imaging across different scales. For example, in the sub-micro scale, we have the fluorescence microscopy and also optical resolution photoacoustic microscopy. And over faculty also have the super resolution and also the two-photon microscopy imaging setup. In the macro level, we have the OCT and also acoustic resolution photoacoustic microscopy imaging setup. And at the tissue level, we have the homemade photoacoustic imaging setup and commercial ultrasound imaging setup, and also macro CT with and also the fluorescence molecular imaging setup for small animal imaging, particularly the mouse and the rats. Besides the neuroimaging platform, we also have molecular imaging platform. We also have the neuroimaging platform. Our neuroimaging platform consists of 4 cores. The first core is the neuroimaging core. It's considered a lot of 12 FNIS functional near-infrared spectroscopy optical neuroimaging setup. And we also have 12 EEG setup, including the FMI compatible EEG setup. And the second core is the brain intervention core. We have the TMS, RTMS, and ultrasound interventional setup. And the third one is the core is we call the behavioral data collection call. It's actually this kind of sender useful to collect the behavioral data from animal to human being. The last one is the high performance computing call. We have the high performance computing center in the it's a part of China high performance computing. We call the cloud. With southern part is located in Macau, actually, a southern part of China. And recently we entered the 3T FMI, Siemens Prisma 3T FMI, basically used for the animal and also human being neural disorder and other cognitive neuroscience studies. Here actually focus on the language study. It's a really social science, but I'm very interested in this kind of study. And also you involve the Portuguese, the Chinese, and English translation, and also the brain cognition across the bilinguals, and also the addiction, behavioral addiction, such as gambling, gaming, and also decision making. And we also child development, aging, and brain disorder, and also, of course, also technically related to the neural imaging, particularly also the optical neural imaging, right? Is my strength, actually. Then I give some introduction to the background of this presentation. Actually, this presentation is for cancer therapeutics, right? We know that cancer actually is one of the leading cause of the mortality and also mobility around the world, right? So if we use the imaging technique to achieve cancer early detection, also achieve the image-guided therapy, we can improve the survival rate of the patient, and also can actually reduce the side effect during the treatment. NIH published data show that if breast cancer, right, is detected under the stage 1 or stage 2, right, the 5-year survival rate can be up to 100%. So that's why we need to do the cancer early detection and also achieve the image-guided cancer treatment. And we know that for traditional biomedical imaging techniques, such as the CT, MI, right? It's kind of structural imaging technique cannot achieve cancer early detection because of the low sensitivity, right? No functional information. And also very hard for this kind of imaging technique to achieve simultaneous cancer treatment and also cancer detection, right? Additionally, actually for cancer treatment, we have the surgery, radiotherapy, and also chemotherapy. Recently, very interestingly, we know that phototherapy, right, is attract a lot of attention, extensive attention, because it's non-invasiveness, right? It's a technique. It also can be carried out locally, right? Based on the locally selected area, cancer, very target area, and also is actually all lower, have the lower drug resistance, right, and also lower side effects. That's the advantage. Among other image techniques developed that have been to resolve the basic limitation of the lower sensitivity of CT and MRI, right? Photo quantum imaging is particularly very interesting and also promise, right? It's a very promising technique because it can achieve simultaneous functional, molecular, right? And also structural imaging. It can also achieve the neural imaging, functional neural imaging. That's a very interesting technique, and also with high resolution, high contrast. So I just show how the photoquantum works. When we find the lead pulse, right, the photon will be propagated together in the beginning, then the photon will be diverged in the diffusion domain. When the photon reach 2 or 3 up to 1 millimeter, right, to reach to the diffusion domain 2 or 3 centimeter, right. So the photon will be absorbed. Some photon will be scattered, right. Some photon will be transmitted from the surface of tissue. When the photon are absorbed by the tissue, it will generate heat. So the heat will generate acoustic wave. So the wave will propagate to the together. The acoustic wave will propagate to the surface of tissue, where they are detected by the ultrasound array, right? So based on the measure the photoquantum signal, we can actually achieve the functional imaging, right? To recover the functional information with high optical contrast. So photocoder show the advantage where the challenge, particularly for the label-free photocoder imaging, right? For label-free photocoder imaging, generally we use the visible light or the first window light to illuminate the animal or the tissue, right? So generally it will reduce the penetration depths. So that's the one issue. The second issue that photocoder imaging, label-free photocoder imaging, they use the optical contrast. Optical contrast is very good for imaging the soft tissue, including the blood vessel, right? But it's very hard for the photocoder imaging to recover the functional and the structural information of the hard tissue, for example, bones, right? And other soft tissue with lower contrast, right? So it's very hard. So we have to use the multiple contrast and develop multiple imaging setup to resolve this kind of issue to recover most of the tissue, right? From soft tissue, hard tissue, right? And also increase the blood vessel. And also label-free photocoder imaging technique is sufficient for high sensitivity, cancer detection, because so that's why we need to use a nanoprobe, a contrast agent, to improve the resolution and contrast and the sensitivity, right? And also achieve, molecular imaging gadget cancer treatment, right? And so that's a big challenge that is here, right? You can see that we need to use the multi-modality imaging technique, right? We need to develop the multifunctional nanoprobe as a contrast agent for multi-modality molecular imaging. And also this kind of nanoprobe also serve the phototherapy agents for photodynamic thermotherapy agents, right? Sometimes it can also serve the chemotherapy agents, depend your design, right? Depend on your requirement of your the treatment. And we also need to actually perform the second near-infrared window photocoder imaging. That means because the second window can near-infrared light can improve the penetration depth of the photocoder imaging technique. Right now, actually, basically, there are three categories of the photocoder of contrast agent for cancer theranostics. The first is a small molecular, right? It's we overlap have also done a lot of work on that. The second one is the inorganic nanoprobe. The third one is the organic nanoprobe. Today, I will show two very representative nanoprobe for multifunctional near-infrared second near-infrared nanoprobe for the cancer theranostics. The first one is the inorganic, right? The second one is the organic nanoprobe. The organic probe we use the polymer dots. Because they have high good, biocompatible property, and also it's also have a small size, and also has a lower side effect, and also has high optical absorption property, can be used for simultaneous photocoder imaging, and also can serve the current agent for simultaneous photocoder imaging and also photothermal and photodynamic therapy agents. The first one is we call it is inorganic nanoprobe. We call it is a GA functionalized carbon sulfur nanoprobe for dual mode photocoder imaging and MRI imaging near the second near-infrared window. So this image show is a schematic show of the how the GA functional BSA modified carbon sulfur nanoprobe can be used for the dual mode molecular imaging and also for the cancer treatment. So this basically BSA with a cation and anion, right? With under the condition of the pH value higher than 7 and also heat, right? We will produce the triangle BSA modified carbon sulfur nanoparticles. Then GA will integrate to the nanoparticle to generate the GA functionalized carbon silver nanoparticle, right? This nanoparticle has a multiple function. It can be used for, so the GAR actually serve as the counter agent for MR imaging, right? The carbon silver nanoparticle, they have high optical absorption, which is very broad absorption band, right? Can be used for the optical or photocopic imaging in the visible window, and the first window and the second infrared window. So it has a lot of functions. So then we do the we show the how we do the calculation of the conjugate functional carbon silver nanoparticle, right? So we can see that this is the TM image, right? Show the size and also the shape of the nanoparticle. This one actually show the absorption spectra, right? For the produced nanoparticle. We can see that the peak is in the second near-field window. And this one actually show the optical spectra before and after they got conjugated to the carbon silver nanoparticle. And we also do the dynamic lattice scattering measurement, and also this and we also do the in vitro test, right? Show that actually the probe, right, really can improve the contrast agent of the photocopic image and MRI image. You can see that the photocopic signal and the image, right, increased with increased concentration of the nanoprobes. And also the nanoprobe actually show that it has a lower toxicity to the cells. The cell viability is the test show the efficacy of these nanoprobes. Then we do the image, right? So this is the photocopic image, and this is the MRI imaging. So photocopic image, we only image the tumor area, right? We can see that after we inject the nanoprobe through the TV, right? Intravenous TV injection of the conjugated carbon silver nanoparticle, right? We can see that the photocopic signal image, right? The contrast agent actually was enhanced from before the injection and after post-injection, and 6 hours, 12 hours, and also 24 hours, right? So basically the photocopic signal also show the enhancement increase, the signal increase, right? And the different time points. Simultaneously, we can also see that photocopic signal also show the increment, right? Increase. We can see the signal also increase from before the injection, after the injection, right? And the contrast agent also we can see that is significantly improved after we inject the contrast agent. Actually, we can also see that for MR imaging, right? If you just do the label-free imaging, right, it's easily to miss the tumor, right? Because generally the contrast agent for the tumor, the contrast for the tumor area, right, is smaller than the surrounding tissue. So that's why I need to do the multimodality molecular imaging, right, to really improve the sensitivity, detection sensitivity, right, to improve the sensitivity, resolution, and also basically sensitivity for cancer detection and also to get the treatment. Histology analysis also be performed, right? We can see that it basically we can see the nanoparticle basically show no damage to the normal tissue, right? We compare to the control group, right, PBS. So that show the efficacy and also show the performance of the developed multifunctional nanoprobe. Again, we also show a very representative nanoprobe, organic nanoprobe, right? That's the PDOTS. Recently, we published this work. It's a new work we just published actually last month. We know that actually organic nanoprobe, they show a lot of advantage, right? It's a high absorption, very good, excellent biocompatibility, right? To tissue, right? So it's a lower toxicity, right? And high absorption surface. So it has a lot of advantage compared to the inorganic nanoprobe. So we can see that this is a structure of the DPP, BTD, TD organic probe, right? So that show the second image show how the DPP, BTD, TD nanoprobe are produced and used for the catheternotics. For this project, actually, we produced two PDOTs. The first one is actually, we call the S PDOTs. It has ultra small size, only 4 nanometer. It's easily to can be extracted quickly, cleaned from the body, right? And no, actually, it will not store in the body. No, actually, no damage to the to the normal organs. The second one is we call the LDOTs. This kind of PDOTs has the diameter of 25 nanometers, right? So we can we want to do the comparison to show really is the ultra small nanoparticle can improve the the metabolic capability, and we want to inspect whether it can quickly clean from the body, right? And so this is show the dynamic light scattering signal image figures, right? We can see that the size, right, around 4 nanometer. The second one, PDOTs, we call the LDOTs, is sized around 25 nanometer. And the theta potential, we also did the theta potential, and also the optical spectrum show that the peak of the optical absorption is located in the second near-field window, right? So we can see that the peak. And we also tested the photothermal property of the derived ultra small nanoparticle in the second near-field window, right? So this one show actually the photothermal heating curve, right, with different power of the laser. And this one show that the photothermal image, right? Photothermal actually image and photothermal image and with different concentration of the nanoprobe. And then this show the temperature evolution of the ultra small nanoparticle with different concentration, right? And also the circles, right, on and off for the photothermal therapy. And then we also have this kind of photothermal performance, right, to compare with water, right? Water can show the photothermal property of the PDOTs. And then we do the in vitro photothermal therapy test, right? Photothermal test of the cancer cell based on the derived ultra small PDOTs. So basically, without laser, right? Without laser irradiation, we basically did, we can see that most of the hairless cancer cell, right, when they incubate with the PDOTs, basically it is show no damage or toxicity to the cancer cell, right, during 24 hours and 48 hours. But when we use the laser irradiation, right, and also without irradiation at the control group, we can see that most of the cancer cells were killed. And also confocal imaging also performed with nanoparticle, with laser or without laser, right? So without laser irradiation, when the hair cell were incubated with the nanoparticle, right? So basically, most of the cancer cell will survive, right? So the green one actually show the live cell, the red one show the dead cell, cancer cell, right? But when we use the laser to remove the cancer cell without any nanoparticle, right, it's basically also the cancer cell survive. But when we use the with the laser irradiation, and then we increase the nanoparticle concentration, we can see that most of the cancer cell began to die. Some become dead, right? Some particularly with this concentration, right? Most of the hairless cancer cell were dead after irradiation, right? Within 5 minutes. Then in vivo test, photocoated imaging test were also carried out. We can see that basically photocoated signal increase with the increased concentration of the nanoprobe, right? And we also compare the photocoulter imaging capability between the two PDOTs. One is ultra small PDOTs, we call it S PDOTs, right? We can see that this is the photo imaging, the tumor tissue, right? Before the injection, and then after post-injection, and 1 hour, 0 hour, right? 1 hour, 2 hour, till 24 hours. And then we also do the photocoulter imaging for the big size LDOTs, right? 25 nanometer LPDOTs, right? We can also see the photocoulter signal increased, right? But we can see, but it's different, right? For the ultra small PDOTs, the signal can increase quickly, right? We can after 2 hours it reach the peak, right? But for the large size nanoparticle, right, it can basically take a couple of hours to reach the peak. And we also do the photothermal therapy, right? It shows the photothermal ion image, right? Thermal image for after we inject the SP dots, right? And do the photothermal treatment. And the second group will show actually the contrast group, right? Didn't show the temperature increase. This one show the temperature change, the image, right? And then also compare the temperature evolution between the different groups, right? Control group PBS, right? PBS with laser irradiation, SP dot without laser irradiation, and with P dots, SP dot with laser irradiation, right? We can see that only this group, ultra small SP dots with laser irradiation, it show the temperature increase, right? To up to 55 centigrade, right? And we also do the photothermometry for different groups, right? The 4 groups. And we take the photography and day 0, day 6, and day 14, right? And then we also compare the tumor volume based on different treatment, right? We can see that only the ultra small PDOTs group with near-infrared, second near-infrared laser irradiation show they reduce the tumor volume, right? The red one, right? And also the body actually weight didn't show significant change across the different groups. And finally, actually, I want to show that actually the PDOT actually really no damage, right, to the normal tissue, normal organs. And you can show, this is the large size PDOT, this is ultra small PDOT. We can see that after 3 days, right, the ultra small PDOT can quickly extract from also the organ or the body, right? So, and also valued by the blood signal. We use a lot of blood Luton index to show the metabolic property of the PDOT, ultra small PDOTs. So I want to quickly finish my presentation because it's very late. I think, okay, I want to take any question. Oh, no, we don't have question, right? Okay. Welcome to visit our campus, right? Macau is a very nice place, very multicultural European style city in Asia. I think and people are very nice. And we don't have so far we don't have the virus, right? No people got infected so far. Previously, 4 months ago, we have several patients, but actually it's imported from other area, but all of them are recovered right now. So it's a very safe place. Okay, thank you.
All right, thank you so much, Professor Yuan, and thank you for your presentation. Also, thank you for your invitation. So everybody, please go to Macau and find Professor Yuan, okay? He will be very happy to be our host. So we have come to the end of today's presentation, and I would like to thank all speakers for today. And for myself, I've learned a lot. And the take-home message today, I think, is that there are many ways to solve a problem. And the solution might be a simple molecule that can be found around us. And although nanomedicine is not a magic bullet that could solve all the problems, but by integration of various fields, I think it will become one of the most effective ways that could interfere with many points or pathways in various diseases. So we applaud all researchers and scientists working hard even to this day to find new interventions for the betterment of human mankind. So we thank you for that. Now we have come to the conclusion of today's conference. We thank you to all the speakers for their time in sharing with us their groundbreaking works. We also thank all of you who are joining us today online. We hope to see you again in our future conference. And with that, we wish you a good evening and